Good afternoon, everyone. This is Xiao from the Southern University of Science and Technology. Today, I will introduce my recent research work, Magnetically-Connected Modular Reconfigurable Mini-Robotic System with Bilateral Isokinematic mapping and fast on-site assembly towards minimal invasive procedures. My presentation consists of the following parts, and first of all, I will introduce the minimally invasive surgery. And this is the Da Vinci robotic surgery system. Because of the robotic system has the advantages of exceptional precision, increased proficiency, and the greater visualization, and the instrument can access hard to reach areas. So robotic minimally invasive surgery can shorten the hospitalization, reduce the pain and discomfort, and so on. Has many advantages to both for the patient and to the surgeons. But some of the surgeons, we need to access a very narrow area, and the target is small, and we need to minimize the robotic system, and the surgery system is more and more required to specialized and portable. So here we propose the modular and the reconfigurable robotic system as shown in this figure. And this is based on their parallel mechanism, and the system has totally 5 degrees of freedom, and the chain of the parallel mechanism consists of the platform and the struct, and the struct connect the platform and the base through the permanent magnetic cylinder and bores. And the outer diameter of the system is only 32.5 millimeters. And the characteristic of this design is modular and magnetically connected, and the joint is replaced with the magnetic ball joint. And this is the developed prototype. It consists of the driver and the control system. The control system is based on the Q8 USB from Quasar. This is a real-time control system that supported in MATLAB Simulink, and the manipulator and the Tele-Operator. And we want to reduce the size of the manipulator, so the manipulator is connected to the driver through this flexible shaft. So we can isolate the drivers far away from the end effector. Here we take some carry out some experiment. The first one is the accuracy test. In this video, we is the cylindric curve tracking experiment, and the right figures is the desired trajectory of the sliders and the mirror trajectories of the sliders. We also plotted the arrows curves. And here is the tracking result of the cylindric curves, and the desired curve is in blue, and the mirrored one is in red. and below is the errors, tracking errors in X, Y, and Z directions. And we also plotted the slider tracking result. We can see that the slider tracking errors is much smaller than the end effector tracking errors. So we can see we can say that the errors mainly induced in the chains. And here is the spherical helix curve tracking, and we also displayed the desired trajectory, mirror trajectory, and errors. And here is the tracking result of the spherical helix. Both the and the effector trajectory and the slider trajectory are plotted with arrow curves. We also tested the load capacity of the proposed system as we connected the end effector and the base with magnetic ball. So we have to test the load capacity of the manipulator. First of all, we tested the static load that the manipulator is placed tighted with 45 degrees, and it can bear a load of 150 grams. And we also tested the horizontal position and the vertical position, and the load is 120 grams and 500 grams respectively. Besides, we also tested the dynamic load capacity in X direction, Y direction, and in Z direction with a circle curve. And the load capacity is shown in the figures. And this is the Tele-Operation demonstration. And for easy of control, we designed the system with bilateral isometric mapping characteristic. So the manipulator has the same configuration. So when you operate the teleoperator, the manipulator will has the same motion with the hand motion input. And this one is the on-site assembly. We can fast on-site assemble of the endoscope, the scissors, and the grippers. And here is the conclusion of our proposed system with existing device. For example, IRB and S650HS and the Pocket Dirt and the laminated dirt robots and the mini dirt proposed by Robert J. Wood. And the last one is ours. When compared with the size, weight, and the workspace, and payload, and accuracy, and we have some advantages, and we also have some disadvantages, and we will improve it in our future work. We also proposed another cable-driven, based on bottom cable-driven left right-hand manipulation system, and we want to use it in eye surgery and in left right-hand micro manipulation. And imagine we have a portable robotic surgery system that is small enough that we can use it in future in military application, and we can also use it in space because we need to save space and weight when you are in space. Okay, that's all. Thank you all. And I would like to thank all of the authors for their contributions. Thank you for your attention. Thank you.